Hey guys, welcome back to Verilog playlist. Let us see some more Verilog concepts in this video. Starting with the Verilog module, as we know, Verilog start with the keyword module and it contains input-output ports. The Verilog module we are writing here for a hardware design, that hardware input and outputs are will be called as input and output ports. In Verilog, we are going to start writing the code with the port declarations. As you can see here, output of ALU module. So the module ALU is the name of the module and output 32-bit OUT out is the name. Inputs are A and B with 16-bit and clock and enable are single bit inputs. So if the input is more than 1 bit, we need to declare it as a vector. That's why it is 15:0. It means A will be containing or having 16-bit value and also B. Similarly, out is having or holding 32-bit value. And then after the declaration of these input and output ports, we need to write the logic for this ALU. So that will be consisting of a data flow statements, or it will be a instantiation of lower modules. It can be always and initial blocks also, and some task and functions if it is required we are going to write. So this is the general structure of a module, and here in the example we have shown only input and output port declarations. And if you look at the ports, input and inout are declared as wires. Generally these two are wires here. You can see input A, B and C are wires. Output can be a wire or it can be a register. If we are declaring or writing our Verilog code in a behavioral description style, the output should be a register. Similarly, if you are designing for a combinational circuit, you are using assign statement and writing using a data flow model, then we are not supposed to declare it as register. All these concepts we see in the next video. Here, just let us understand input and outputs are declared as wires, but output can be a register. And there are two types of declarations you can see here. This first one is a Verilog 1995 style, means it is the conventional style we are going to write. First, in the module definition, we list out the ports over here with a semicolon. Then after we are going to declare each and every inputs and outputs like this. Otherwise, you can combine the port declaration as well as port definition like this. Module S2 within the braces, you are going to declare all the input and output ports with their port direction. So this will be called as ANSI C style. Both styles you can use, any of the styles you can use in your design. Coming to parameters, you can see here in the block diagram, there is a parameter list can be added after the port list. That is for declaring constants. If you are going to use any constant value, something like in a module, A size will be 32. Wherever you are going to use this A size, that will be holding a value 32. So in these cases, we can make use of parameter in Verilog. These parameters means declaring constants. And these values also can be overridden when the design is compiled. At the compile time, we can override those values also. And the syntax for that is parameter is a keyword and name of that parameter and the constant we are going to write. You can see here parameter 2 down to 0 is the size for this idle as a name. It will be having a value 0. Since it is a 3-bit, we are giving the value as 3 tick D0. It means 0 is a decimal. With 3-bit representation, we are assigning that to idle. So throughout the module, idle will be having a value 0. And the default value need to be set at the declaration time itself. And by default, it will be a 32-bit value. You can set any width to the parameter. But if you are not going to mention the width, the default will be 32-bit. And you can see here, you can declare a parameter inside a module like this. Once you are going to declare all the input and outputs over here within the braces, then you can declare a parameter. Otherwise, you can declare at the module header itself. Module, the name of the module, and the parameter list over here with a hash. And then after you can declare register wires and all. There are two methods to declare a parameter. You can follow any of these. Then if you look at the port declaration, how we are going to declare the ports by looking at the block diagram of our design. This is the adder which is of n bits wide. It will be having A, B and C in as inputs, S and C out as outputs. Here this is a n bit adder, but we are going to design this for 8 bits. Then what we are going to do, parameter n is equal to 8 we need to set as a parameter, it is constant. So then you can declare the input and output ports with this n as input vector size n minus 1 down to 0. It means 7 down to 0. This is how we can make use of a parameter while declaring the ports. And similarly in the ANSYS C style, the parameter will be declared before the port definition with the hash keyword like this after as soon as you write the module name. So these are the two examples, the different ways of declaring the ports and the parameters. Then comes instance of a module. You can use one module inside a other module as a subcomponent. It is like creating a full adder using two half adders. So half adder module you are supposed to design first, and you can make use of that half adder to design a full adder. You can see here instance of a module, how it will be. Instantiation is a process of just calling a module from the other module. So the syntax is like, you need to first write the module name. Then if there is any parameter list you need to pass with a hash, you need to write the parameter list. And then you need to give a user defined instance name for that. And then you need to map the ports accordingly. So module name is a name of the module to be instantiated. Suppose in full adder, if you are using half adder, the module name of the half adder you are supposed to write here. Parameter list, if you have set any parameter, you need to declare here. Then instance name can be any instance name. Suppose in the full adder design, if you are using two half adders, you need to give the different instance names as half adder 1 and half adder 2. And then port list for the connections. And now the port connections can be done in two different ways. One is port can be mapped by using the named connection. We can use names of the ports and we can connect, or else we can go with the order in which we have declared our ports in the modules. It is like, you can see my module hash dot w of 1. Here w is a parameter defined. While instantiating that, I am passing 1 as an value for that. Similarly, n is an parameter. And this is the instance name. Then here in1, in2 out are the input ports in my module. I am instantiating that and connecting to the top module to A, B and C. This is how we can connect the ports to the instantiated module to the external module. Similarly, by using the order we can connect. Here W, N is the parameter declared in the order. We are just passing the value 1, 4. 1 corresponds to W, 4 corresponds to N. No need to write the names over here. But here the thing is, we need to follow the same order. If 4 is written first and 1 is written next, 4 will be assigned to W. Similarly, the ports also A, B, C we have written. The A corresponds to in1, B corresponds to in2, C corresponds to out. Suppose if we rearrange this, the mapping goes wrong. We need to take care of the order here. Then if you look at the example code of full adder design using half adder. Here I have taken half adder as example. Here half adder is giving the sum and carry by taking A and B as inputs. You can see input and outputs are declared. Assign sum is equal to A XOR B and carry is equal to A and B. This is data flow style of writing the Verilog code, where we are going to use the assign keyword. When you are going to use the assign keyword, the outputs declaration should be a wire, it should not be a register. So here I have not declared sum and carry as register. Now by using this half adder, I am designing my full adder. I know that A and B can be input for the half adder and it will give C as carry and S is sum here. Sum I need to pass as input to the next half adder and carry I need to take it further and the carry of the second half adder will be taken into OR gate to generate the full adder carry. Similarly, sum will be the output of the second half adder by taking sum of the first and Cin. So you can see here the input and outputs of the full adder is declared here, and I am instantiating my half adder here. This HA0 corresponds to the first one. Half adder is the name of the lower module, half adder module, as it is. HA0 is the instance name I have used. And here I am mapping dot A. This first A corresponds to my half adder A that connected to input A. If you can see here, this half adder will be having A here, and this will be connected to A of full adder. Similarly, B corresponds to B. Sum is S. This S is a wire. Here I have declared this S is a connection between two half adders, and this is not my port of a full adder. It is just a connection between the two half adders. That's why I have defined this S as a wire. And similarly, I require two more, C and C1, as a carry of the two half adders. That's why you can see at the end of these two, carry will be mapped to C in the first half adder, carry will be mapped to C1 in the second half adder. So this C and C1 are taken for OR gate and carry will be generated. Here the two instances are half adder instances, and I am using assign statement to generate the carry. This is how we can use the submodule, and we can instantiate to develop the top module. Here full adder becomes top module and half adder is a submodule. Then you can see one more example here. There is a top block. Within the top block we have ALU, we have mem, and within ALU again we have FIFO. Now I am defining module top. Here we need to write the port list, and then I am instantiating ALU and memory over here. ALU is U1, mem is U2, and we need to connect the ports accordingly. And similarly, there is a module of ALU separately and module of mem separately, and FIFO also separately. This FIFO I am supposed to use within ALU. That's why ALU contains FIFO again. This is how we can divide the top module into submodules, and we can develop the submodules first, and then we can map that to the top module by using the instantiation. And the port directions. If you look at the port directions while connecting this to the top module or to the external world as a test bench. If you can see here, Verilog design for a full adder contains A, B, C in as inputs and output as sum and carry. This is our design. Externally, we are going to write a test bench, and this test bench is going to give A, B, C to my design as input. That we call it as a stimulus. Stimulus come from the test bench. In the test bench, my input A, B and C in becomes registers, and outputs sum and carry becomes wires. The rule says if it is an input in the design, it is a net type or what we call it as wire type, it will become register or net in the to the external world. So here test bench is the external world. Inputs A, B, C in becomes registers. Similarly, if the output is declared as a net or register, net in the sense output itself, it is like a wire, or if we can use it as a register, then it becomes wire, means net in the external world. If it is an input output in out, here in the Verilog design also it is act as a net, outside also it act as a net. There will be no declaration of a register for that. So this rules we need to follow while writing the port declarations or the port directions to the external world. Now let us see a simple test bench for a half adder design, and let us see how the ports are going to be mapped and how the stimulus is going to be given. Design, this is the design code, and then this is the test bench code. Module half adder is the name of the module. A, B, sum, carry are the input and output ports. Here I have defined. And assign carry is equal to A and B, assign sum is equal to A XOR B. So this gives me the design of the half adder. To verify this, we can write the Verilog test bench like this. Module half adder TB is the name I have used, and I am declaring my inputs AB as registers and similarly output as wire. This is what the rule says. And I am instantiating this half adder over here. DUT is my instance name and I am mapping with the name, port names. Dot A corresponds to my design port of A, that is register A. You can also use reg x comma y over here, that doesn't matter, but dot A corresponds to x, dot A of this becomes x, dot B, this B becomes y if you are going to declare registers as x comma y. In the similar way, you can assign sum as S here, carry as C here, and as your need. And then comes the stimulus generation. We need to declare or give the values for AB using initial begin block. Within the initial block, we can assign the different values, and for the different values, we need to give the delay. This will be executed one after the other. A is equal to 0, B is equal to 0 will be executed. Then after 10 time minutes, A0, B1 will be executed. After 10 time minutes, A1, B0 will be executed. It means this statement will execute after 10 time minutes. This statement will execute after total 20 time minutes. The next statement will be assigned after 30 time minutes. So this is how the delays will be calculated. And then I have used a system task, that is $monitor here. This gives me a display in the console or in the log. How it will display? $time, this fetches the simulation time, and within the double quote I have written how the string need to be displayed. A is equal to percentage B is going to fetch the value of A over here. B is equal to percentage B will fetch the value of B. Similarly, some carry will be put it over here. And I am going to get the output in the console or in the simulation log as A is equal to that. First, it will give the time as 10 nanoseconds. What is the value of A, B, sum and carry. And here I have given only 4 delays and only one initial statement, initial block. Your test bench may contain multiple initial blocks, and if any clock is there, we need to generate the clock over here, and you can give different set of inputs, and also you can randomize the inputs and give in the test bench. So this is some introduction to the Verilog. With this you can start writing a Verilog code and implement any of the design using data flow description. And in the next video, let us see how the data flow and behavioral description code look like, and how to use if else case statements and all. Thank you.